All right, welcome back to the whiteboard. Today's explainer is your ultimate survival guide for Module 2 of Engineering Mechanics. Look, rigid body statics, friction, and beam analysis can honestly seem incredibly daunting at first glance. But I promise, once we start breaking down the visual patterns and the underlying logic, it's all going to snap right into place. Let's dive in. Now, we all know the exam stress is real, right? So today, we are skipping the fluff. We are hyper-focusing exclusively on those heavy-hitting 14-mark numerical questions you'll see in Part B of the syllabus. By the end of this explainer, you're going to have the exact visual frameworks and structured techniques you need to bag every single one of those marks. Here's our game plan for today. We'll quickly hit friction foundations, visualizing connected bodies, the classic ladder problem, couples and coplanar forces, and finally, beam support reactions. Okay, first up, friction foundations. First off, you absolutely have to have the angle of friction locked down in your mind. Think of it as that critical, high-stress tipping point right before an object just gives way and slips. Formally, it's the angle between the resultant reaction and the normal reaction when a rigid body is on the verge of sliding. Being able to visualize this angle helps you understand exactly when the static friction in your system is totally maxed out. And honestly, you can't talk about that without mentioning the angle of repose. This is a crucial concept to pull out of your back pocket whenever an exam question throws an inclined plane at you. Imagine you're slowly tilting a ramp with a block resting on it. The angle of repose is the absolute maximum angle you can hit where that block stays in perfect equilibrium without sliding down. And here's a fun fact: if your ramp angle exactly equals the angle of friction, you've hit the angle of repose. So these concepts are what directly anchor Coulomb's laws of sliding friction, basically the absolute rules of the game for setting up your equilibrium equations. Keep these bullets in mind. Friction always fights the direction of intended motion. It depends heavily on how rough the surfaces are, but kind of surprisingly, it's practically independent of the total contact area. And the real key for your math, the frictional force is directly proportional to the normal reaction force. Moving right along to Section 2, Visualizing Connected Bodies. Now check out these setups on screen. This perfectly illustrates what they actually love to throw at you on test day. When you encounter connected bodies or wedge setups like these, the biggest trick is observing how friction acts uniquely on each individual block. In that first setup, blocks A and B are connected on a slope. In the second, block A is sitting right on top of block B while a force yanks on it. You cannot, I repeat, cannot, treat them as one giant combined mass. You've got to draw separate free body diagrams to see how the friction of block A specifically pushes back against block B. Which brings us to Section 3, the ladder problem. This one is an absolute engineering rite of passage, isn't it? The setup is classic. You usually have a person climbing a ladder that's leaning against a rough vertical wall and sitting on a rough horizontal floor. Your job as the engineer? Figure out exactly how far that person can climb up those rungs before disaster strikes and the ladder slides out from under them. So, let's break down the strategy to crush this problem every single time. First step, draw a flawless free body diagram. You need to completely isolate that ladder from its surroundings. Second, and listen, this is where I see so many students bleed marks. Pay super close attention to your coefficients of friction. The wall and the floor almost always have different friction values. Don't mix them up. Finally, you just systematically apply your 3 equilibrium equations. All right, shifting gears from friction for a minute, Section 4, Couples and Coplanar Forces. Let's define a couple. In mechanics, a couple is this really specific, fascinating force system. It's made up of 2 equal, opposite, and parallel forces that do not share the same line of action. And because their linear push and pull exactly cancel each other out, what you're left with is pure, unadulterated rotation. Take a look at this whiteboard sketch. It really brings that rotational concept to life. See how forces F1 and F2 are acting vertically but in completely opposite directions at different points on the body? These unlike parallel forces create a rotational moment, a twisting effect, that you absolutely have to account for in your analysis. If you miss a couple in your math, I guarantee your entire system is going to be wildly off balance. And finally, Section 5, Beam Support Reactions. Okay, look at this beautifully chaotic beam setup. When an exam throws a simply supported beam at you that's loaded up with a bunch of stuff, like this 10 kilonewton point load, a 20 kilonewton load, and then that tricky angled 15 kilonewton force sitting at 30 degrees, don't panic. The methodology to untangle all of this is completely formulaic. You secure those 14 marks by sticking to a strict logical sequence. Step 1. Draw your free body diagram, making sure to replace the physical supports at the ends with reaction forces. Step 2. You have got to resolve any angled forces, like that 15 kilonewton load, into their vertical Y and horizontal X components. Remember your basic sine and cosine geometry. You can't just drop angled forces into a simple vertical sum. And step 3, once everything is neatly aligned in X and Y, deploy your equilibrium equations to solve for those unknown support reactions. As we wrap up the core concepts of this explainer, I seriously want you to mentally screenshot this strategic checklist for rigid body equilibrium. Number 1, always start by isolating the body with an FBD. Next, identify all applied loads and support reactions clearly on your drawing. And finally, remember the master key, the moment equation. Setting the sum of moments to 0 is so incredibly powerful. By cleverly choosing the point where you calculate your moments, like, say, dropping it right on top of a support with unknown forces, you instantly eliminate those unknowns from your math, cracking the whole problem wide open. Before you go hit the books again, I want to leave you pondering this. What if your professor threw a hybrid high-yield question at you? Something combining both ladder friction and beam reactions into one giant mega problem. Picture a ladder leaning against a wall, but it's resting on a dynamically loaded beam. How would you isolate that system to find your first critical moment? Think about how the normal reaction of the ladder acts as just another point load on the beam. Keep this visually structured approach in mind, trust your free body diagrams, and you're gonna absolutely crush those exams. Thanks for checking out this explainer with me, and I'll see you in the next one.